So I'm Sebastian Fischer, and this is my colleague Uwe Lang.
Hello.
We are both software engineers at Bosch GmbH. And beginning or end of last year, we basically open sourced our first project, Kiso-testing. Why the title rides a bike, not a bug? We are also both from the division e-bike. And Kiso-testing was basically used, or is used, to test the entire new generation of e-bikes. And we'll give you a deep dive into it. And my mouth is not working. Works. So why did we develop PyKiso? So at the beginning, 2 years ago, we were trying to find out which framework could we use to enable the developers to test the new generation of e-bikes. And when we scanned basically all the frameworks available, we realized there are only some to do unit tests on target. We can name Unity or Zephyr or Pigweed from Google, or full black box system test. For example, we use Selenium or sometimes Robot Framework. But as embedded software engineers, I'm always struggling with integration. Integrating, for example, because we have an e-bike, of the CAN stack, or maybe a higher protocol stack on top of the CAN stack. And I'm not able, with these two extremities, to test exactly my integration. The other point is, in case of a smart device or IoT device, probably the only way or the only interface I have to my device is a wireless communication. BLE, LoRa, Cat-M1. So I need to be able to test this one really well, to do a hard smoke test, see how it reacts with a lot of load, etc. The last point is, if I'm able to have or cover partially some features, I could maybe provide this piece of test code to sub-system tester or to system tester. In this way, I could also enable the rest of the V model to release the software and the new component faster. So how does it exactly work? So here, a standard development setup. In our case, in the middle, BDU is a drive unit. And on this drive unit, we can see 3 ways to connect to it. On the top, that's the debugger. It's a Lautobar debugger. It enables me to, after compiling my application, to flash it on my hardware, debug it with, etc. Bottom left, that's the power supply. My hardware needs power to run. I could also play to see what happens if it runs. I shut down the current. And for us, the only real communication layer we have is CAN. That will enable us to have all the communication with the rest of the system. Let's say now, okay, I have my 3 connectors, and I know I have access with the debugger, so maybe I could simulate or fake the speed sensors. And maybe I simulate or fake them in a way that the drive unit believes it's driving 15 kilometers per hour. I know my only interface through CAN, because we want higher protocol. We are using a so-called UDS protocol. So maybe I request via UDS, okay, what is your speed? And if the integration of all my elements there works well, I expect to receive 10 kilometers per hour. In PyKiso, it's called auxiliaries. So how does one level under PyKiso works? PyKiso have 2 steps. The first one, based on some configuration, it generates a virtual test setup. It's basically a representation of the developer board, and this virtual test setup provide APIs that can be used on test level. Yeah. And the second step would be PyKiso executes this test using this virtual test setup. For developers, it has 4 exact steps. The first one would be the declaration of this test setup. There are 3 parts inside. The first one would be the declaration of the auxiliaries. Maybe it's a little bit too small, but I declare an auxiliary called aux1, which will have as connectors the communication chan1. As configuration, I have none. And of type, it will be a device under test auxiliary. This type is very important because it's informed to PyKiso and will enable after which API will this aux1 provide to the test. I declare aux2, aux3. Second step, connectors. And I can declare here chan1 for my channel 1, configuration none, and it's of a type example communication channel. I declare all my connectors, and at the very end, I declare which test suite are running on this virtual test setup. Yeah. In PyKiso, the idea is you cannot exceed or you cannot execute tests if your hardware is not enabling you to execute this test. So we go with the principle, first you declare your test suites, and then you need to find out how to test with this auxiliary or this virtual test setup, which is now available. Part 2, write tests using the test setup. This happens also in Python. First part, I will import PyKiso, and from auxiliaries, I will import the 3 auxiliaries I declared here, aux1, aux2, and aux3. And after, for the second part, I follow a standard testing procedure. I declare my test suite setup, my test suite teardown, and within it, I declare a set or a certain amount of tests I will want to execute there. You can declare on top, like define test parameters, the idea of this test suite, and also, when it comes to the test case, the case ID. That enable at runtime or when you start to define which order the test will run or be executed. I would like to look with you at the 2 last parameters here, test IDs, that enable you to have in the reports containing the information, maybe which requirements does this specific test case implement. That enable us, if we use, for example, TestRail or JAMA or any requirements management tool, to have a link direct between the requirements declared there and the test that was executed. The last parameter is the tag. You can declare in which condition you want this test to run. And this is free for you to define. For example, here I have branch level, daily, nightly, that enable me, if I have so much tests that it takes 4 hours, maybe for a pull request, I just want 30 minutes test to run, and when I do a release 4 hours, so I'm able then, through this tag, to define which test runs when and how. Third is run the test. So this is a simple command, PyKiso -c and the YAML file from the beginning. And I can extend behind with several parameters, for example, --junit that will tell PyKiso it needs to generate an XML report. And this XML report can be imported into Jenkins, and the result can provide information about how much tests succeed, were skipped, failed. Yeah. So I will pass to my colleague Uwe that will maybe give you a more deeper insight how we are using it with an e-bike.
Okay, thank you, Sebastian. So I will give you a small introduction how we test an e-bike. So the goal which we follow or which we pursue at eBike is that we meet our test requirements for our different departments, which are for our departments with one unified framework. Currently, those departments are the components teams, and we also have the integration teams, which are always testing on the bike and boxes, which is actually all bike components together, and they're the complete e-bike as the components. So for all our stakeholders, we want to empower the developers, also the component developers, to write tests which are actually able to run everywhere. So in practice, this means that a developer, in the best case, has the test setup on his desk, and then the developer connects to the test setup with his PC and is writing tests for it. After he makes sure that the test is working and running as expected, he's normally pushing those tests into the repository. And at that point, the test will be used to run at our, through our CI pipelines, which we are using currently Jenkins. And as I said, the test script, PyKiso actually makes sure that the test which we execute runs always in the same way. Even if we have a developer PC which runs on Windows, and on our device farms we are using actually smaller nodes, which is here the Raspberry Pi, and also runs on a different platform like Unix, which is actually very valuable for us because with those small devices we are easy to scale up our test farm. So on the next slide. Yeah. Thank you, Sebastian. Of course, if any one of you downloads the PyKiso framework, it would be not possible for you to write tests with it for an e-bike. For this reason, we created an internal repository, which we call EB plugins, and the EB plugins extends the PyKiso framework to make it able that we are able to test the bike. So especially we add communication auxiliaries because actually all of our protocols are proprietary, and we also add auxiliaries for custom hardware because we have also custom emulators. It's, for example, the ABS speed simulator. And what I want to show on the slide is that PyKiso is actually quite easy to extend with the needs which we have at eBike. It also runs very efficiently, so that's the reason why we can run it on smaller devices like a Raspberry Pi, and also with the EPL license, this allows us also to easily to scale up. Okay, to the next slide. Here we can see how we really test at eBike. So on the left side you can see the server racks which we have, that they are located currently in Custoding, so it's a room full of those racks. And inside those racks we have those drawers, and inside those drawers we could have single component setups, and we could also have a complete bike in the box. Here in this example we see two Raspberry Pis. Each of them are connected to a PCAN connector or to a Lauterbach connector, which we call connectors also in the PyKiso framework. And those connectors are then connected to the device under test, which is currently here the battery. As said, our setup goes currently into the hundreds. So for each pull request, which we, also for each development step, we are really running all those tests through our pipe with Jenkins. And what's also quite cool in our device farm is that even if a developer don't has the test setup on his desk, he can easily connect to the device farm. We have separated nodes only for those processes for development and testing. And he can easily connect to those nodes, run or write his scripts on the Raspberry Pi itself, and can also run them there. That's also what we have made possible. Okay, we also brought to you a little demonstration to you. That's what we like to demonstrate is a test case which we call Walk Assist. So our bike provides a feature which is called Walk Assist, which allows you, which is actually helps you to pushing the bike. In the normal use case, you would press the down button and hold down the down button, and then you have to push the bike or even tilt it, and then the bike will give you torque support. This becomes quite handy if you imagine if you're standing on a really steep hill and you want to push the bike upwards, because an e-bike is a little bit heavier than a normal bike. Okay, then I will run my demonstration on my laptop. So on my laptop we have the Kiso framework. We are actually able then to communicate with the bike. We are also able to communicate other components, so we could have cut off the other components, but in this case we are pushing interactions into the system, so it's quite more an integration test, and we are at the end verifying if we got walk assist from the bike and if we can see a bike speed. Okay, I see Sebastian is already preparing it.
So maybe for a demonstration, without the automation, right? When I switch the bike on, yeah, if you had once or drove once an e-bike, you can basically hold the minus button, which will lead the bike to a walk assist mode, but it's not doing anything. It's a safety function, right? And I just need to push it a little bit, and then he will start pushing himself. I don't know if you see. And now the point is demonstrating exactly this feature, but with a test framework.
Exactly.
The idea is to show that actually also with Kiso, with an e-bike context, we are verifying safety critical functions within the e-bike.
Yeah. To simulate the SCC signal, we are actually overriding the internal ACC sensor signal. So I would like to start the test now. As I said, it will now press the button and hold it for several seconds, and then it will override the sensor signals. And so Sebastian is only holding the bike and he's not pressing a button. And I hope it's working, right?
Does it?
The tricky part is that we need a server authentication with the Bosch network.
Yeah. Now I see the walk assist switch is on. And oh.
Yeah, and it's working.
Basically, driving itself. They will not drive all the way through because we may not be able to stop the motor on time to do that.
Okay.
Yeah.
Sebastian, then I give the words back to you.
Yeah. Thank you. So here, yeah, we definitely show the features that are available within e-bike, but what is important also to show you what is contained today in the open source project. So there are 3 pillars available. There is a core, which contains the runner and the generator, test suite setup, generator, etc. There are the auxiliaries that you can just plug in, that are already available open source, and there are the connectors available. So as core feature, we also already extended to the robot framework, so we are supporting it within the robot framework, and we are also supporting it within PyTest. Yeah? So you could use PyTest if you like this testing language to, instead of the standard Kiso, you could do that. Within the YAML file, you can already declare environment variable. Yeah? For example, the Raspberry Pi and your personal PC or professional PC may have different paths to access, I don't know, some library. Yeah? So you can, in the configuration file, in the YAML file, for the configuration of a specific auxiliary, define, okay, please get for this one an environment variable A. If this environment variable A is not available, I can also extend it, saying as default value, just take this. The multi-tag inputs, like in the test, if in the tag section you defined tags, you can add a parameter when you call Kiso to filter which test should run and which test should not run. The next one is access to test configuration. We had the case, for example, we have different boards or different versions of the BDU boards. Yeah, we have the C sample, the D sample, so different versions. Yeah, and between these two, maybe in the configuration there is a slight difference. It will be a shame to rewrite the entire test suite or to copy this test suite if the change is just about one small parameter I could maybe do in the test suite setup. Yeah? So for that, you can, within your test, import the YAML configuration, but also import what was provided as parameter in the command line interface. That allows you to have the information that allows you to have this slight different test suite setup. Yeah. The next one is a proxy capable for connector sharing. So here I have a specific PowerPoint. We're mostly CAN focused, so it will be another CAN example. Over CAN, there is different protocols supported. Yeah, there is UDS, but there is also, for example, XCP. Yeah. But the CAN dongle you see here is actually exclusive. So as soon as one library takes over this connector or this dongle, the other library cannot do that. So it basically limits you. You can only test the UDS or the XCP. But if you have features, because the device is allowed to contain several protocols in parallel, and you have features where you have to test this too, you cannot do it normally. The proxy enable you the proxy will basically have the exclusivity over the CAN connector. And then on top, you can plug a UDS auxiliary and a XCP auxiliary, for example, and suddenly on your test level, you can use both in parallel and do tests with both. The next point is Python package requirements. You can also, in this config YAML file, define which Python versions or which Python libraries versions you need. If we provide, for example, the next PyKiso version, a new feature, and your tests are relying on this new feature, you can specify, okay, I cannot allow PyKiso version lower than this one. YAML composition, we had cases where maybe we want to declare in one specific YAML all the connectors, in another YAML all the auxiliaries, and in a third one connect everything together. You can also do it. And the last one is what we are using specifically in our case. Right? At the moment, you fulfill the auxiliary interface or the connector interface. You can simply declare it in your YAML, the path to this auxiliary you declared, and it will be automatically taken in consideration for your test. Today's auxiliary we support, which are open source, the instrument control. It allows you to control a Rot and Schwarz or power supplies if they have an Ethernet connection. UDS, the server part and the client part. The acronym is some kind of hardware that enable you to play with a USB connection, so you can remove in a USB connection the power or cut the USB connection or switch it. The recorder is simply, like the name said, recording something on a specific bus or a specific connector if you give him a connector. And that enable you also a little bit, if you have a test and you wait from your device maybe a warning message, it can parse, you can give him the information, and when this warning message is there, you can use it to validate your test or say it's a failure. Yeah. And very soon we'll also support the fire test. It's changed name, I don't know if Zephyr or it's a very big IoT real-time operation system. Yeah. And this way, if you have already in Zephyr or Zephyr tests, you could combine it with PyKiso to test maybe your communication layer. Yeah. You could run one test there and verify that the messages are sent correctly over BLE. On connector level, today we have the debuggers, so the Lauterbach and the Seger. On CAN, we have PCAN, Vector, so PCAN dongle, Vector dongle, and for Linux users, Socket CAN. Internet TCP US, UDP, Serial UART. VISA is a specific protocol for the instrument controller. And process, with a process, you can start a process on your PC and have a channel with it and request some elements and receive from it elements. What is planned for the future, our roadmap? We are very feature-driven internally right now. So we basically collect inputs and transform these inputs in some auxiliaries, connectors, or additional functionalities for the core and contribute that. But we do not have enough external user to define a nice roadmap, what, when, and how. We still have wishes, and as soon as we have some more time, we will work on them. We would like to support Arduino. We would like to support SIGWID too. Internally, we also have test apps developed that enable us to also do unit tests on target. We have one available in C++, and we need to bring it open source. And the next one is a test app for Rust. We also would like to do. So, last PowerPoint, that's us. If you want to get in touch with us, Kiso-testing dev@eclipse.org. Kiso-testing reads the docs for our documentation. Our open source project is on GitHub in Kiso-testing. And on Stack Overflow, if you combine Python, integration test, and continuous integration, we don't have enough point to create our own label yet. But as soon we have it, there will be also a Kiso-testing or PyKiso label in Stack Overflow. So that's it. We hope we wake your interest. Yeah, thank you.
Thank you. Are there any questions?
So, any questions? No?
Okay.
Yes?
I have a question not strictly related to the testing. You said test app for Rust. Why? Because you internally use Rust or because now Rust is...
There are internal discussions about using at a certain point Rust. And there is a small community that wants to more and more use Rust within e-bike, and if we have the test app available for them at this point of time, it will be a gain for them to do their testing too. As it's a timing topic, seeing. Yeah. Okay.
Okay, then. Thank you.
And thank you.